Poisson started investigating and thinking about civil and criminal trials and jury systems in France in the 1830s. And he objected to the Laplacian idea that a defendant should be equally presumed to be guilty or innocent. Poisson then introduced a two-parameter model, the first of which was a parameter capturing the guilt or innocence of the accused. Suppose then that an accused individual is guilty a proportion theta of the time. Theta is the probability that the person in the dock is guilty. In a technical language, we can think of theta as being governed by a Bernoulli variable z, which takes value 1 with probability theta and 0 with probability 1 minus theta. Z then is an indicator of guilt. When it is 1, the person is guilty. When it's 0, the person is innocent. Poisson was acutely aware that theta should not be considered fixed for all time. That in a tranquil society, we might well anticipate that theta, the probability of guilt, is bigger than a half. Presumably, in a tranquil, well-ordered society, prosecutors don't just drag stray innocent people and throw them at the mercy of the courts. In other words, there's a presumption that due process was served, that the prosecutors brought people up before the courts for good and sufficient reason on the basis of validated suspicion. But of course, in turbulent times, like the French Revolution, this may not be the case. And in cases like that, you could have theta less than 1/2, which signals a much more chaotic society where individuals are dragged to the courts willy-nilly. So here is one parameter, a parameter theta, which at least at the time at which the court decisions are being made, should be considered to be fixed at least temporarily. It's a parameter of the problem. Nominally, we should hope it is larger than 1/2. The second parameter was, of course, the Laplacian parameter that juror decisions based on the evidence presented to them are not always certain, that juries can make mistakes. Let P represent the probability that a juror errs, makes an error, does not evaluate the data in front of him properly. Again, technically, we can think of labeling or tagging an error through an error indicator, a random variable x, which represents a Bernoulli trial with a success probability p. X is 1 if an error was made, 0 if an error is not made. In a well-ordered system and in well-selected juries, one would hope that p is less than 1/2. A juror is more likely to get it right than to get it wrong. Of course, the quantity p could vary from jury to jury. But as a matter of modeling in a sanitized world, we could imagine that p is essentially fixed for the veneer or the pool from which the jury was drawn. A factor here is that the evaluatory capability of the juror is considered to be independent of the guilt or innocence of the accused. So you have two parameters specified independently of each other. Now let us see where this kind of modeling will take us in 19th century France. In the years between 1825 to 1830, juries in France were comprised of 12 individuals, and conviction required a vote to convict from a strict majority from at least 7 of the jurors. We now have a principled setting, a sanitized model in which we can query the efficacy of jury verdicts. So, to begin, what is the probability space for jury verdicts? Now imagine the years are between 1825 to 1830. We have a jury of size 12 and a defendant who is accused. The defendant is either guilty or not guilty. This is a parameter z, an indicator variable z, which indicates guilt or innocence. The theta here is going to be capturing the efficacy of the prosecutorial system, how well law enforcement works in a given country at a given time. Now, bear in mind that the jury are not a priori cognizant of the guilt or the innocence. So the value of Z, the guilt or the innocence, is known to, let's say, an oracle who is establishing the ground rules for this chance game. The oracle says guilty or innocent, and then the jurors hear evidence, and you have 12 jurors, and each of them comes to a decision, either correct or incorrect. Naturally enough, let's tag whether the juror made an error or not by a sequence of indicator variables x1, x2, x3 through x12 for each of the 12 jurors. And what do these variables indicate? Well, Z indicates whether the person is guilty or innocent. x1 through x12 indicate whether jurors 1 through 12 made an error or not. What is the natural probability measure? Clearly now we have a setting where it is natural to posit repeated independent trials. Z is a Bernoulli variable, a guilt indicator with a success probability theta. Each of the x's are Bernoulli variables, error indicators with success probability p. Of course, we are viewing the success of a coin toss in a rather perverted and twisted way. Success for Z means that the person is guilty. Success for the x's means that the jurors made mistakes. But no matter, it's a coin toss. A natural model here is to posit that these are all independent trials. Now, it is not unreasonable, perhaps, to posit the independence of the Z from the x's. Guilt or innocence versus the ability of a juror to logically and coherently evaluate information, data presented to them. The x's, well, if one postulates there are different people with different mindsets and independent faculties, then again we have a natural notion that the x's are independent. The assumption here, of course, is that they're all sharing a common error probability p. Okay. If we start to write down the probability measure for the ensemble, now we've got a list of 13 ones and zeros, which represent guilt or innocence followed by error or correct decisions. From here, naturally a majority vote simply tabulates the votes of the jurors. And so a natural question then is, how many errors are made by the jury as a whole? Well, this is of course simply a sum of x1 through x12. Each x is a 1 precisely when that juror makes a mistake. And so the sum of the x's tells you how many jurors are in error. This, if you recall, is what we called S subscript 12, a sum of 12 terms. And because we're adding Bernoulli trials, the result is going to be a binomial distribution characterized by 12 tosses of a coin, whose success probability is p. To summarize, the guilt indicator Z is a Bernoulli variable. It takes value 1 with probability theta, 0 with probability 1 minus theta. The x's are independent juror error indicators. They take value 1 with probability p, hopefully less than 1/2, and take value 0, they make a right decision, with probability 1 minus p, hopefully bigger than 1/2. And the number of juror errors conforms to a binomial distribution. In our notation, the mass function for the binomial is denoted b with a subscript 12 for the number of trials, the success number, k, the number of errors made, and the success of the coin toss, p. Okay, we now have a probability measure. We know it's a product measure. What are the relevant events of interest here? Naturally enough, there are two that we need to focus on. The first, a fundamental question, is the accused guilty or innocent? Let G represent the event that the defendant is guilty. let I, the complement of G, naturally represent the event that the accused is innocent. So two fundamental linked events. What else can we think about? Well, naturally, whether the individual was convicted or not. Let C denote the event that the individual was convicted by the jury. Recall, for conviction, the jury needs 7 or more votes to convict. And let A, the complement of C, denote the event that the accused is acquitted. Now remember, of course, an event is a subset of the sample space. The sample space is a list of Bernoulli variables, a guilt indicator and 12 error indicators. What is the event G? Well, G occurs precisely when the indicator of variable Z is 1. It is independent of the choices the jurors make. Therefore, all sequences which begin with a 1 will be precisely the event that we call G. And of course, the event that we call I, that the accused is innocent, refers to all sequences in this chance experiment which begin with a 0. What about the event C, that an accused is convicted? Now recall that in a jury process, conviction is by a majority, and you need an outright majority voting to convict to be able to convict that individual. Well, there are two cases here. What if the individual were actually guilty? Now, of course, the jurors don't know this ahead of time, right? They're going to make the decisions based upon the evidence presented to them. But suppose the evidence is presented about an individual who was guilty. In this case, a conviction will happen if there are fewer than 5 errors in decision. If a juror gets it right, then he will properly have concluded that the individual is guilty. So as long as the number of jurors who get it wrong, who conclude that he is innocent, is 5 or fewer, then you'll have a majority of 7 or more jurors who agree that he is guilty, and the person will be convicted. And therefore, in the case when the individual, the accused, is guilty, conviction occurs when the sum S12, the number of jury errors, is no more than 5. What about if the individual were innocent? Now, in this case, conviction will occur if 7 or more jurors get it wrong. If the individual is innocent, and if 7 or more jurors conclude that he is guilty, then in fact he will be convicted. And therefore, in the case when the individual at hand is innocent, conviction occurs when the sum of juror errors is 7 or more. Of course, now we can readily transcribe this into what kinds of sample points fit these criteria. Okay. At this point now, we're equipped to begin an analysis of the problem, and we shall turn to this next.